Alright, in this video we're going to look at the circular time reversal property of the DFT, and this will help us to understand how circular convolution works. So first of all, what I'm showing here is a list of numbers from 0 to 7. These are going to be the time indexes into a sequence of length 8. And here I'm showing what the time reversal of these numbers looks like when we take them modulo 8. So this notation here where we put a parenthesis around a quantity and then put a subscript, a number subscript on the parentheses, that means take these numbers modulo 8. This is a notation that's used in our textbook. So the numbers in natural order go sequentially from 0 to 7. Now let's look at the time reversed version of these. So 0, negative 0 is still 0. 0 mod 8 is 0. So that first sample doesn't change. Then when we put in a 1, negative 1 modulo 8 is 7. You take 1 plus 8, that gives you 7. That's in the range from 0 to 7, and so we stop there. 2 plugging in, we get a negative 2 modulo 8, that gives us a 6. Negative 3 modulo 8 is 5, negative 4 modulo 8 is 4, and so on. And the thing that I want you to notice here is that when we do a circular time reversal, or a modulo n time reversal, the first sample stays where it is, and all of the other samples in the sequence get reversed. Notice that this sequence is 1 through 7, and this is 7 down to 1. So if we had a signal that took on the values A, B, C, D, E, F, G, H, if we were to do a circular time reversal of that sequence, it would be A and then H, G, F, E, D, C, B, which is just the reversal of the rest of the sequence. So in a cyclic time reversal, the 0 indexed sample stays put. All the other samples are reversed. So let's see how we can then derive the time reversal property of the DFT, exploiting these ideas. All right, to begin, we're going to assume that a sequence x of n has a DFT given by x of k, and here's the Dft Analysis Formula. Now if we start to dive in and ask the question, what is the DFT of a time reversed, circular time reversed version of our sequence? Well, to figure this out, what we're going to do is just simply plug in to the DFT transform formula, and then let's go ahead and start by pulling out that first sample from the sum. Why are we doing this? Well, it goes back to the ideas that we were just talking about. In a circular time reversal, the first sample stays the same and all of the other samples get a reversal. So we're going to take that first sample and treat it as a special case. So we pull it out of the sum and leave all of the other terms in the sum. And then notice what's happened here. We went from a modulo n index to an index that looks like this. And this encodes that time reversal, but without the modulo notation. Notice that when we put n equal 1, we get capital N minus 1. And when we put little n equal 2, we get capital N minus 2. And that, again, is performing that circular time reversal that you see on the previous page. Okay. Now we can look at a few of these terms. First of all, we take a look at this one and we realize, oh, that's just equal to 1. Why is that? Because we have 0 in the exponent, and any number to the 0 is going to be 1. And then we can do a change of variables on that next sum. So I'm using the change of variables here. Little m is equal to big N minus little n, so we can substitute that in here. And then if we solve for little n, we get big N minus m. If we substitute that into the exponent, we get two terms. this term, which we recognize as being equal to 1. Why is that? Well, it's the e to the j 2 pi times an integer, so that's equal to the real number 1. And then we have this extra term. If we look at the limits, when we plug little n equal to 1 into this sum, we get capital N minus 1. And then when we plug capital N minus 1 in, we get 1 out. So the limits are going to stay the limits on the sum on m go from 1 to n minus 1, just like before. Now let's take another step. What we've done here is just eliminated this last complex exponential because it's equal to 1. And we need to make this thing look like a Dft formula, like we see up above, which has a negative in the exponent. So to do that, I took this plus and decomposed it into 2 negatives. The next step is to put a modulo n subscript on this negative k. And we're doing that because we're looking forward to trying to re-express this as some function, some relation to capital Xk. So the modulo will help us to protect that. The other thing that we've done is we've reabsorbed that 0 index term into the sum. Why is it that we can do that? Well, remember that when m is equal to 0, this complex exponential is equal to 1. And so we can freely bring that term back into the sum, and it doesn't change. We don't need to add anything special for it to accommodate it. And then we look at this and we recognize, oh, that's just the Dft evaluated at negative k modulo n. And so we've derived the time reversal property of the Dft. In summary, if you do a cyclic time reversal in the time domain, you get a cyclic time reversal in the frequency domain for the Dft.